Okay, I hope that you all got your feet wet and were not too discouraged with chapters 1 and 2. I noticed on the test that for the most part, everyone did fairly well. There were a couple of things that I noticed that we need to work on a little bit. One of those are significant figures. Some of you were putting all of the digits from the calculator in your answer. And now that was one of the topics that was covered in these chapters, especially chapter 1, where it said the rules for significant figures. When you multiply or divide, you may have as many digits in your answer as there are in the fewest. Now, I will deduct points in this chapter and moving forward every time. So please follow those rules. If you are given 3 numbers in your given or in the equations, that's how many significant figures you're permitted in your answer. So pay attention to things like that, please. That's just standard procedure in chemistry or in any science discipline, to follow those rules of significant figures. I also want to caution you again, you're going to have to use the math launcher on your Blackboard. Please, if you haven't watched that how-to video, please do so, because I'm going to deduct points each time that you do not use your subscript correctly. And we're going to be using a lot of formulas, and you're going to have to be entering that in. So please, if you have not done so already, please learn to use that math launcher on Blackboard. And I'm going to probably do another how-to video, because I'd like for you to learn how to use the rest of the math launcher. There's another tab that you can open on that math launcher that will even open how to do like the isotopic symbols and how to do those, and you're going to be needing those later, so I may go ahead and get that for you. But let's talk about chapter 3, which in my mind, chapter 3 is probably the most useful tool that this course will offer for you, and that's stoichiometry. That's how that's pronounced, stoichiometry. And we're going to learn dimensional analysis. You learned it chapter 1 and parts of chapter 2. But it is one of the most useful tools. I've been teaching a long, long time, and I've taught a lot of math courses. I've taught everything from college algebra, calculus, all the way down. And I've also taught every science course that's in the physical sciences that's out there imaginable. So I know how important this topic is when you're in this kind of discipline. And so we're going to sit on this and spend some time here. And I urge you to get the technique down correctly. And I may go a little bit different than Dr. Burge does, simply from my experience of knowing how students best grasp the material. We're going to start with finding what our molecular and formula mass is. Now, please do not get these two mixed up or get too bogged down in calling them molecular masses and formula masses, because there's just one name that you can lump the two together, and that's what I'm going to do. Also, we're going to be learning about percent composition of compounds, and percent composition is very useful, especially if you're brought some unknown substance and you're asked to identify it. Percent compositions can be quite useful. Then we're going to go into equations and how we can use stoichiometry in chemical equations, and we're going to learn what a mole is and how it's used in chemistry and molar masses. And then we're going to talk about combustion reactions and calculations that use the balanced chemical equations to go with it, which means we're going to learn how to balance equations, and then we're going to learn what a limiting reactant is. So these are the topics. There's a lot of math in this chapter. This is probably the most intensely math-heavy chapter that we'll cover. All right, we're going to start with molecular and formula masses. If you were to combine the two together, molecular and formula masses together would be called molar mass. And molecular masses would be masses of molecular compounds, compounds that are covalently bonded, that you would use prefixes, carbon dioxide, disulfur pentoxide, those kinds of things. You would call them molecular masses. And then formula masses would be ionic compounds, things that contain polyatomic ions, tertiary compounds, those kinds of things. You would call them formula masses. But you can lump the two together and call everything a molar mass. And it is defined as the mass of 1 mole of a substance, or the mass of a mole of, well, any substance is called a molar mass. But if you're just talking about one molecule of it, or one formula unit of it, one smallest piece of it, then you would just call it, it's either it's a molar mass or it's formula mass. And that's what we're going to talk about. And to find these two things, you're simply going to use the atomic mass from the periodic table. That average atomic mass that we learned to calculate in Chapter 1, where you took the percent abundance of it, and then you multiplied it times its actual atomic mass, and then you averaged all that together by its weighted average, and it's what's on the periodic table. That average atomic mass, it is the only mass that's given on the periodic table. If you will take those, and then we take the molecular formula, or the molecular formula, or the chemical formula, whichever you want to call it, then we can find the mass, okay, the chemical mass of that. Its units are going to be atomic mass units. Now I want to clarify this. This is if we are talking about one single smallest piece. Now I want to make sure that that's very clear to you. In chemistry, you have to keep in mind this right here is the smallest piece of water that exists. Please do not think that hydrogen is the smallest piece of water that exists, because if you're just talking about hydrogen being the smallest piece of water, by itself hydrogen does not make up water. You have to have 2 hydrogens and 1 oxygen all bonded together to have water. So the smallest piece of water that exists is a chemically bonded H2O molecule. It has to have this structure where there's our O and there's our H and there's our H. This is a water molecule, individual, and it's the smallest piece that exists. So if we wanted to find the mass of this molecule, it would be called a molecular mass. And to find it, you're going to use the periodic table, and you're going to recognize, hey, I have 2 hydrogens present, and I have 1 oxygen present. Okay? Well, if I have hydrogen, I have 2 of them. Each one has, from the chart, this is from the chart, the periodic table right here, each one of them has this atomic mass. And it's, since I'm dealing with each individual atom, remember the unit for that is AMU, and so that is going to be 2.016. And then how many oxygens is in water? 1, so 1 times, and that average atomic mass from the periodic table, it's actually 15.99994, which rounds to 16.00. So that's going to be 16.00, and you add those together and you get 18.016. There is your average atomic mass of water in AMU. And so that's what you would record as your correct mass. Okay? Let's see. Yeah, 18.02 is what they have for that. All right? I don't know why it did me that screen like that. That's where she got the 18.02 from. added those two together. That's how you do it. All right? And then the same thing is true about an ionic compound. Now, what it's saying here in this slide is that, let me see, I'm waiting for it to slide, it's being slow. Although an ionic compound does not have a molecular mass, because ionic compounds can dissociate so easily, we would say it has a formula unit, a smallest piece still. So we can find its formula mass, and you're going to do it in exactly the same way. Now, here's your example problem, and this is a sample problem that's listed for you in your textbook on page 80, I do believe. Where it's asking us to determine either the molecular or formula mass when appropriate. So it gives you those three to do. And you're going to work them each the same way. And so let's work just one of them, and then you can work the others. I'm going to do the last one, C, for you, because it's the most challenging. Please notice this 2 that's outside, right there. That 2 is going to get distributed. We're going to distribute that 2 here, here, and here. It will not go to the barium because it's not inside parentheses. So that's what it reads right there. So on the periodic table, we're going to need barium, we're going to need carbon, we're going to need hydrogen, and we're going to need oxygen. How many bariums are there? 1. How many carbons are there? Well, there's 2 times 2 is 4. See that? There's how many hydrogens? There's 3 there times 2 is 6. And there's oxygen. There's 2 here times 2 is 4. So you have a total of 4 oxygens. And each one of these bariums, according to the periodic table that I'm looking at right now, says 137. I'm going to have to skip over these arrows that I drew. 137.327. And we have 4 times each carbon is 12.01. Each hydrogen is 1.008. And each oxygen is 16.00. And then you're going to multiply those out. That 137 stays there. 4 times 12.01 is 48.04. 6 times 1.008 is going to be 6.048. And then 4 times 16 is 64. And then you're simply going to take and you're going to add each one of those up. So you're going to take the 137.327 plus 48.04 plus 6.048 plus 64, and you get 255.415. That would be, and that's in AMU. So this is 655.415 AMU. And please understand what that is. That is the mass of one formula unit of barium acetate. That's what that represents. All right? I believe that's pretty straightforward. I'm going to give you plenty to practice with those. All right. Traditionally, I've always told my students that you should round your atomic masses to 2 places past the decimal, because you're going to notice on your periodic table that most, not all, but most of the masses go to 3 places, but some just go to 2. So that's what I let my standard be, is the 2 places past the decimal. Like in this letter C here, it goes to 2 places, 3 places, 2 places. Now the barium on this one, it just goes to 1 place past, but on mine it went to 3 places past, which is why I chose the smallest number, which was 2 places past the decimal, and that's what I rounded mine to. All right, Section 3.2 is percent composition. And percent composition is exactly what it says. It's percents. And you know how to do percents. I hope by this point in your life you know how to do percents. And percent compositions are useful in finding or like if you're finding iron ore or things like that and you have a larger sample, you can predict how much is going to be in that sample, for example. All right, so to find percent composition, here's what you're going to do. You're going to first of all find the mass of the substance, the molar mass, just like we just talked about doing. Find the mass of the substance. And then if you are looking for the percent of the element hydrogen, I used water first, so let's stick with water. Then you're going to say, well, okay, water has a molar mass of 18.02 grams, or AMU. So what's the percent of hydrogen in that? Well, hydrogen, how much mass does hydrogen have in that 18.02? So you would take hydrogen's mass and divide it by the 18.02. And then since we're dealing with percent, that means per 100, then you're going to multiply it times 100 to get your percent. Now, in this example that she gives on this slide on section 3.2, she's using hydrogen peroxide, not water. But it's going to be the exact same thing. You see the formula that she gives you. To find the percent by mass, you find out how many atoms of that element do you have times its atomic mass and divide it by the either molecular or formula mass of the element. And then you're going to multiply it times 100 to get your percent. We're going to work an example. I believe if we worked an example, you're going to be able to understand this much better. So let's do that. It asks us to calculate the percent composition by mass of lithium. Here it's actually asking us to do lithium carbonate. So that means it's asking you to do every single element in lithium carbonate. So step 1 is to find the formula mass. Now, I'm not going to take the time to show you how to do that again because that's exactly what I just did. I showed you how to find the formula mass. So we have 2 lithiums, which is they've done that right here, and that's the molar mass, the atomic mass rather, of lithium from the chart. If you look on your chart, your periodic table, you'll see that lithium number 3 is 6.941. That's its atomic mass. And then you have 1 carbon, and that's its atomic mass from the periodic table. You have 3 oxygens. Each one has an atomic mass of 16. And so this is my lithium right here. This is my carbon right here. This is my oxygen right here. Add those all together, that's my atomic mass. Okay? So then step 2. To find my lithium, percent lithium, I'm going to take lithium's mass, which is going to be 2 times the 6.941. So that's 13.882 divided by the molar mass, the formula mass rather, 13.89 AMU. Multiply that times 100. And you're going to get 18.8% lithium. Okay? You're going to do the exact same thing for carbon. To find your percent carbon, it's going to be what is my mass of carbon. You only had 1 of them, so 1 times 12 is 12.01. I'm going to divide it by the the formula mass, which was 73.89 AMU. Multiply that times 100, so you can 12.01 divided by 73.89, and you're going to get 16.3%. 6% carbon. And you're going to do the exact same thing. 3 times 16 is 48 divided by 73.89, and you're going to get 64. 48 divided by 73.89 times 100 gives you 64.96, which is 65% oxygen. Okay? I ran off the screen. I know that's a hot mess, but that's exactly what you're going to do. Okay? That's all I'm going to do for right now because I've gone so long on my PowerPoint, but you're going to see that that's exactly how Dr. Burge did that right here, and I'm going to give you plenty to do. So that's sections 3.1 and 3.2 from your text.